Okay, so we were discussing alpha decays, and two important observations I pointed out. One is that if you calculate or measure this Q value of the reaction, some A x z going to A minus 4 y z minus 2 and plus 4 H E 2 and then plus energy. If you calculate this Q value using semi empirical mass formula or from the known masses of nuclei, you find that for A somewhere around say 150 or so, this Q is positive. So, all nuclei having nucleons, number of nucleons more than say 150 or 145, the Q value of this reaction is positive. That means, if they decay through emission of alpha particle, and they will be saving energy, rest mass energy. So, rest mass energy decreases in this, and therefore, spontaneous alpha decay is energetically possible. So, that was one. Another thing we saw in that N versus Z diagram, that you do have stable or nearly very nearly stable nuclei somewhere up to say 210 or so. Beyond that, of course, you do not have any stable nuclei confirming to this conclusion, but around say 150, 160, 170, 180, you do have large number of nuclei which do not seem to go through this spontaneous alpha decay. So, that was one observation we pointed out, and the other observation was about lifetime and Q value relationship between these two. So, we found that typically Q for the known alpha emitters, typically Q varies between say 4 MeV to 9 MeV, and corresponding lifetimes, if you look at it, it goes from some giga to microseconds or even less. So, there is a huge range of lifetime, and it is related with this Q. Smaller the Q value, smaller the energy available to this alpha particle, larger is the lifetime. That means, decay probability is small, and as Q increases, the lifetime decreases, and the point to be seen is that this varies only by a factor of 2, whereas this varies by a factor of say 10 to the power 24, 25, 26 and so on. So, very sensitively it depends on Q value. Now, to understand this, we started describing what we call barrier penetration theory or Gamma's theory, which was put forward 1928, early days of quantum mechanics. So, some semi classical calculation, some quantum calculation, basic idea taken from this barrier penetration thing. What we said is the potential, you have a nucleus, this parent nucleus, and you assume that in the parent nucleus you already have this alpha particle preformed. Okay. There will be a probability of alpha particle getting formed, but let us take it that this alpha particle is already formed and will stay here, and it will move inside the nucleus, it will try to come out, and so it remains intact. So, when it moves and it reaches this surface, it tries to come out, and then we looked at the potential, and this potential was something of this sort: V this side, R this side, two regions you can mark when alpha particle is inside the nucleus, when alpha particle is outside the nucleus. When it is inside the nucleus, nuclear attractive force is important, which you can estimate by some kind of squirrel potential of some depth, typically say minus 35 MeV or so. So, it is a attractive potential well, and then once it is outside, it has Coulomb interaction, dominating Coulomb interaction. So, that Coulomb interaction will be 1 by r type. So, you can approximate it in this type of function, where this part is the Coulomb part. This is that barrier height, this is that barrier height. The energy available to this system, alpha particle nucleus system, is this Q. So, this is the region from here to here that is classically forbidden, where the total energy is less than the potential energy, and if alpha particle has to come out on this side, it has to go through this barrier tunneling process, and that is where quantum mechanics comes in. We calculated, or we started to calculate the probability of this alpha particle coming out of this barrier on this side, and that was P is equal to, probability is equal to e to the power minus 2 integration gamma r dr, where gamma r is square root of okay 2m over h cross square, and then this height, this difference, the amount by which it falls short of this potential. This is V at r and this is q. So, V r minus q, and this is 2m over h cross square, and then V r is Z1 Z2 e square by 4 pi epsilon naught times r, and this value q is Z1 Z2 e square by 4 pi epsilon naught 1 by b, and that is all. What is b? Point. B is this point where it comes out of the, so the barrier ends here. So, q is the energy. If you take q as the energy of the alpha particle, then that is equal to the Coulomb potential energy at this point. So, Z1 Z2 e square by 4 pi epsilon naught b is the value of q. So, q you can write it in this way. So, the integration is, your integration we generally write is e to the power minus 2 g. So, that g is equal to, g is this integration gamma r dr. So, 2 m over h cross square Z1 Z2 e square over 4 pi epsilon naught, and then square root of integration of square root of 1 by r minus 1 by b dr, and the limit of the integration goes from this capital R, can write it capital R here. So, capital R to b, the range in which it is in the classically forbidden region. So, from capital R to b here to here is the integration. So, that is this, right. So, now this evaluation of this integral happens to be quite simple, and a simple substitution works. If you write r is equal to b sin square theta. So, this factor here, and this integration I is this integration, this I am writing I. So, I is integration of square root 1 r is 1 by b, and in denominator sin square theta. So, that 1 by b you can take common, 1 by b here, and this will be cosec square theta minus 1, that is cot square theta. Okay, 1 by sin square theta is cosec square theta and minus 1. So, that is cot square theta, and dr is b into 2 sin theta cos theta d theta, right. dr is b times 2 sin theta cos theta d theta. So, that is the integration. Now, I think I can remove this, and this is square root of b, 2 times the square root of b I can write. So, 2 times of square root b here. So, I have taken this b, I have taken this b, and I have taken this 2. This is cot theta is cos theta divided by sin theta cancels out. So, it is cos square theta d theta. So, cos square theta d theta. I will put the limits of theta. This is integration root b you can take out, and this in 2 cos square theta is 1 plus cos 2 theta d theta, and that is square root of b theta here and plus sin 2 theta by 2 under proper limits. So, what are the limits? The limits on r is capital R to b. When r is capital R, then sin theta is square root of capital R by b. Right. From here, when r is capital R, so it is capital R by b and then square root of that, and when r is equal to b, then sin theta is 1. So, theta is pi by 2. So, when you evaluate this integration starting from capital R to b, that g will be equal to square root of that factor will be there 2m over h cross square z1 z2 e square by 4 pi epsilon naught, this factor will be there, and then the integration is square root of b here. So, square root of b here, and then theta plus sin 2 theta by 2. First evaluate at the upper limit, that is at theta equal to pi by 2. So, it is pi by 2 from and plus pi by 2. So, sin pi 0. So, that is all. So, that is the upper limit. Then you write the lower minus lower limit. So, put theta here. So, theta is sin inverse of r by square root of r by b. So, I am putting that lower limit theta equal to r is equal to capital R. So, there theta is sin inverse of that, then plus 2 sin of 2 theta by half sin 2 theta. So, I can remove this part also. So, plus sin 2 theta is 2 sin theta cos theta, 2 goes away, sin theta into cos theta, and sin theta is square root of r by b, and then cos theta, which is square root of 1 minus sin square theta, and sin square theta is r by b. So, it is r by b here. So, that is equal to square root of 2m over h cross square z1 z2 e square 4 pi epsilon naught, and then square root of b, and then you have pi by 2 minus sin inverse, that you can write as cos inverse square root of r by b. So, that is the first two terms, and then you have minus of square root of r by b and 1 minus r by b. So, that is the value of g. So, that is the value of g here, and you can write this at this moment, it is in terms of capital R and B, right. So, this expression is in terms of capital R and B, and what are capital R and B? Capital R is the point where you make transition from that nuclear range to Coulomb range, nuclear dominated range to Coulomb dominated range. So, that point is if this is your nuclear potential well, and here you assume that before that it is inside, after that it is outside, and after that nuclear part is negligible. So, this is R and this height is B, Coulomb barrier height is B. So, B is in fact, if you look at this curve, this B is the Coulomb potential energy of alpha particle with residual nucleus at this capital R. So, you can write this B as Z1 Z2 E square over 4 pi epsilon naught times this capital R, or capital R is Z1 Z2 E square by 4 pi epsilon naught B. What is Z1 and what is Z2? Z2 is 2, the charge number, proton number of helium nucleus, and Z1 is the proton number of residual or daughter nucleus. So, it is, you start with parent nucleus, it is Z minus 2 and this is 2. So, this capital R can be written in terms of this barrier height B. Similarly, what is small b? Small b is the point where Q is equal to the Coulomb potential, right. Q is the Q value, the energy available. So, if that Q here at this point B, where it comes out of this barrier, there Q is same as the Coulomb potential energy at B. So, Q is Z1 Z2 E square and divided by 4 pi epsilon naught times a small b, or small b is equal to Z1 Z2 E square by 4 pi epsilon naught times Q. So, you can write B and R in terms of this capital B and capital Q, this R by B appearing at several places. So, R by B, this R divided by this B is just R by B is equal to capital Q by capital B. Okay. So, we will write this expression in terms of Q and B. So, G is equal to 2 m over h cross square Z1 Z2 E square by 4 pi epsilon naught, and then square root of B, small b, this square root of this small b, and square root of this small b is here. So, it is Z1 Z2 E square by 4 pi epsilon naught capital Q. Then inside bracket you have pi, this is cos inverse, right. So, pi by 2 minus sin inverse is cos inverse. So, it is cos inverse of square root of R by B, and then minus square root of R by B and 1 minus R by B. Oh, R by B is capital Q by capital B. So, write it capital Q by capital B, capital Q by capital B. We are writing everything in terms of capital Q and capital B. We can make further approximations. So, the integration we could do in exact terms, but remember that does not mean this expression is exact, because the whole theory that we are describing from the very beginning is approximate, and even the expression for this barrier tunneling probability e to the power minus 2 times gamma r or gamma dr integration, that also is an approximate expression which can be used if this probability is much smaller than 1. So, you can make further approximations, this you of course, you can take out double of that. So, it is Z1 Z2 E square by 4 pi epsilon naught, that you have double of that. So, square root can come out, and here then you have E, this E square is already gone. So, you have 2m this 2m by h cross square and q, and this side. Now, you can make further approximations if you so wish, because q is typically, this capital Q is typically 4, 5, 6 MeVs, 8 MeVs, like that. Buried height is 25 MeV, 30 MeV, like that. So, Q by B will be small, and if you wish, you can neglect this square term here in front of this linear term. So, if you do that, if you neglect that square term, square of this Q by B terms from here also you should neglect that square terms and keep that linear term, and cos inverse of x is pi by 2 minus sin inverse of x, and if you expand it in series, it is pi by 2 minus x, and then the higher. So, use this approximation here. So, it is pi by 2 and minus. So, cos inverse x is pi by 2 minus x. So, cos inverse of this is minus root q by b, and if you neglect that square term here, it is again minus square root of q by b. So, that is another way of another further approximation. If you want to make quick calculations, you need approximate expressions which can be evaluated easily. So, for that you can use these things. So, you can write this as a double of this, right. So, these two you can combine and you can write 2 times of this. So, that is one version. If you wish, you can go further. This square root of q by b, double of that, and this is pi by 2. Pi by 2 is 1.57, and if q you take 4 MeV and b you take 25 MeV, and if you want to neglect this whole thing in front of this pi by 2, that is also approximation little worse than what we are writing here. In that case, you just forget this, and this pi by 2 can be combined here. So, and then you can use these things. Another way people write it is q in terms of the velocity, speed of the alpha particle. So, you have this expression, and then here this is 2 times mass of alpha particle, 2 times mass of alpha particle, this is h cross square, and this is q value. Now, most of the q value is taken by the alpha particle when it comes out as its kinetic energy. So, this q you can write as half m. So, m by 2 times v square, this capital Q, half m v square. So, half m v square, v is now the speed of alpha particle when it has come out of the nucleus and going into your detector, and then pi by 2 from here. So, you can do this also. So, this 2 and this 2 and this 2 can be cancelled, this pi can be cancelled here. So, all those type of approximations can be done. Z1 Z2 E square by, so these 2 are out and this pi cancels here. So, 4 times epsilon naught, that is from here, and then you have this m also cancels here. So, 2 also cancels here. So, h cross v, it is h cross v, a simple cute expression in terms of speed of the particles. So, various stages of approximations I have described, and then whatever depending on what facility you have to do a hand calculation or a calculator calculation or a computer calculation, you can use the expressions. Remember, all this is capital G. The probability is e to the power minus 2 g, and g you have all these expressions for g. But I would like to connect it to the lifetime. The 2 observations we started with, one is 150 onwards, A is equal to 150 onwards, this Q becomes positive, and therefore, alpha particle is energetically possible favored, but still you have several stable or nearly very stable nuclei somewhere say 160, 170, 180 range. That is one thing which we want to explain with all this calculations, all this theory. And the other thing is the lifetime, relation of lifetime with Q. So, we have reached the, we have to reach the lifetime expression. So, how do I get that? So, you have this nucleus, and in this nucleus if alpha particle goes and hits the surface, what is the probability that it will come out, that we have calculated. Lifetime is related to the decay probability, T half is ln of 2 divided by lambda, where lambda is the probability of decay per unit time. Okay. So, per unit time, what is the probability? This probability of tunneling that we have calculated, this is for one attempt, alpha particle is going here and trying to come out, what is the probability? But per unit time, what is the probability of its coming out? That means, per unit time how many attempts are there? This probability is going to be very, very small. So, that means, the alpha particle commonly will not come out, will be reflected back, it will sent back into the nucleus. But then if it is sent back, it will come here, and from this side if you think that it is going along the diameter. So, it will try to come out from here, and if it is sent back again, then it will try to come out from here. So, in unit time it will make several attempts, and each attempt, this is the probability. So, per unit time what is the probability, and that is lambda. So, lambda is say f into p. P is the probability per attempt, and this f is the number of attempts per unit time. Right. So, this we have done. Now, how to estimate this f? How many attempts it is making per unit time? So, once again we will do a very semi classical or classical type of calculation. If it is going along this diameter and the speed of the alpha particle is some v, and the diameter of this nucleus is 2 capital R, then it takes a time, this corresponding time 2 R by v, going from one end to the other end, and from each end it is making attempts. So, time between consecutive attempts is 2 R by v, and therefore, number of attempts per unit time is v by 2 R. So, this f is v by 2 R, this is different v, remember, let me write it v naught by 2 R. I have used a v here, this v and this v are different, because this is when alpha particle is inside the nucleus, and this is when alpha particle is outside the nucleus. So, when it was outside the nucleus, we said that the energy Q is half mv square. When it is inside, how do I get this v naught? I can get this v naught. Look at this potential energy diagram once again. When alpha particle is inside, this is the total energy Q, this is the total energy, and this is the potential energy. So, if this is total energy and this is potential energy, the kinetic energy is this much. Potential energy plus kinetic energy is equal to total energy. So, this is kinetic energy. So, kinetic energy, which is half mv naught square, is equal to Q plus v naught, capital V naught. This is the depth of the potential is v naught, typically say 35 MeV or so. So, the kinetic energy inside, when alpha particle is inside, is given by this much, and from here you can get that v naught. So, 2 times q plus V naught divided by m and square root of that. And therefore, f is equal to V naught divided by 2 r. So, this divided by 2 r. So, that will be q plus V naught and by m and divided by 2 r. So, I am taking inside. So, it will be 2 here, r square here. So, that is f. So, now I have f, I have p, and I can write the whole expression for lambda, which is f times p. So, g is already here, and I take this expression, whichever level of approximation you want. So, lambda is equal to f, f is square root of q plus V naught and divided by 2 m r square, and then p is e to the power. So, let me write it this way, e to the power minus 2 g, and here is g. Okay, here is g. So, this g will go here. So, that is lambda, and once you have lambda, then T half is ln of 2, which is 693 divided by lambda. So, one can make calculation of T half. So, let me take an Excel calculation and show how this expression, or perhaps one step more of approximation, what kind of values is given for half life. So, Excel. Okay, so you can look at this Excel sheet. I have already fed the formula, but I will just explain what it is. In this particular cell, that is C4, it is written 4 here, and on top of it, it is written capital Q here. So, this is in fact capital Q, that is the Q value in mega electron volts. So, here it is Q equal to 4 mega electron volt. Now, the next cell, if you go here 57.95, that is in fact this is that Z1 Z2 E square by 4 pi epsilon naught, and square root of 2 m by h cross square, and then Q in the denominator. If you look at your board, there is expression for capital G, and in that expression for capital G, you have something outside the square bracket. So, this quantity is that outside the square bracket, and it depends on capital Q. So, capital Q is it is taking from here 4 MeV and calculating that factor outside the square bracket. Then here under the heading of this capital B, this is not barrier height, this is that square bracket expression itself. I have taken that approximation pi by 2 minus that expression 2 times of square root of q by b. So, from there it is calculating this, and in this it is only multiplying these two factors, it is multiplying these two factors and calculating g, this is the g, and here it is e to the power minus 2 g, the probability of tunneling in one attempt, and this f is the number of attempts per unit time. Here it is per second, and this is V naught by 2 into capital R. That expression also you have capital Q plus V naught divided by 2 m r square, square root of that. So, this expression is the formula fed here is just that square root of Q plus V naught divided by 2 m capital R square. So, that gives you number of attempts per unit time. Here is the probability of coming out per attempt. So, you multiply these two f and this e to the power minus 2 g, and you will get lambda. So, that lambda is here, that is the decay probability. And then T half, the half life will be just 0.693 divided by lambda. So, here it is. So, with q is equal to 4 MeV, this T half calculation comes out to be 1.6 into 10 to the power 15 seconds. Capital B, the barrier height I have taken as 25 MeV in this formula sheet. So, 10 to the power 15 seconds. In 1 year you have something like 10 power 7 or so, 10 power 8 seconds, some 3 into 10 power 7 seconds. So, you can convert into years, it will be 10 to the power 7 years. So, that is when q is equal to 4. Let us just vary this q here. This q, let us make it 5. So, we made it 5. All the formula are there, all the expressions are there. We just increase this q value from 4 to 5, and then everything is recalculated, and you can see what happens now. What happens now? Look at this t. This is the T half expression. Now, it is if you go by digits, is 1, 2, 3, 4, 5, 6 digits. So, is 7.7 in 10 power 6 seconds. It was 10 power 15 seconds when q was 4 MeV, and now it has come to this. If you convert it to years, it is 0.24 years. Previously, it was 10 to the power 8 years. So, you can see the sensitivity, q changing from 4 MeV to 5 MeV makes a big change in the half life. From something like 10 to the power 8 years, it has become less than 1 year. Go ahead, make q is equal to 6 MeV and see what happens. So, this 5, let us make it 6. So, now q is 6. So, I am putting that enter button, and q is now 6. Everything is recalculated, and you can see the lifetime, half life. It is only 5.3 seconds. Here it is. It is only 5.3 seconds. So, q going from 4 MeV to 5 MeV, 5 MeV to 6 MeV, this is this half life has decreased from 10 to the power 8 years to 0.2 years, and now only 5 seconds. So, this shows that this theory of barrier tunneling is capable of explaining that particular effect. This is 7. If you want to make it 7, see what happens. Things are recalculated, and see, this is the half life in seconds. It is already 10 to the power minus 5 seconds. Okay. So, this and individually there are 2 factors, that also you can see. This is that factor f, and then this is that tunneling probability. So, both of them you can look at it. The tunneling probability is 10 power minus 20 at this moment, and this number of attempts is 23, 10 to the power 23. So, make this q 4 and see which factor changes most. So, make it 4 again and see what happens to f and what happens to this probability. So, this has changed to 10 power minus 39, and it is still 10 to the power 23. So, this is not very sensitive. It is the barrier tunneling probability which is sensitive and which changes orders of magnitude when this capital Q changes. Okay. So, we come to the board again. So, this is this rudimentary application of quantum mechanics during very early days could explain this vast change in the order of magnitude of this half life, and how sensitively it depends on capital Q, and that was one big victory or convincing application of quantum mechanics, that yes, the world is quantum mechanical in nature, and all this classically forbidden regions and barrier penetrations and all those things are really really natural, and they happen in nature. Now, few more things I would like to tell. We have done all these things taking angular momentum L equal to 0. When even nuclei decay through this alpha mode, this is almost the dominating character, because even nuclei, the spin parity is 0 plus, and when it suffers alpha decay, it is still even nucleus. So, for even nuclei, the parent and daughter both have spin parity 0 plus. So, this is the parent, let us say 0 plus, and this is daughter, which is again 0 plus. So, if alpha particle is emitted, the angular momentum has to be conserved, the parent has 0 and the daughter also has 0, then alpha particle must be L equal to 0. But then you can also have excited states. For example, even nucleus, in this range you can have rotational energy levels. Okay. So, you can have 2 plus, then 4 plus and so on. Alpha particle can also decay to these other states. Now, if does that, the angular momentum of alpha particle cannot be 0. For example, if it goes from 0 plus to 2 plus here and then 1 alpha, consider this transition. Consider this transition, its alpha decays and goes to this first excited state. Now, here the angular momentum was 0 and here the angular momentum is 2, and then you have angular momentum of alpha particle also. So, what should be that alpha particle momentum? That has to be 2 plus. So, that alpha particle must have this momentum 2 plus. What is the effect of that? The effect is to raise this potential barrier by some amount, because if you remember, if you have some potential and L, because of L you have to add L plus 1 h cross square by 2 m r square to the potential. This is the effective potential. If the potential is V r, then this is the effective potential for that R equation, radial equation. So, this potential is raised, the barrier is also raised, and the barrier is raised by the amount L plus 1 h cross square 2 m capital R square. So, you can make a calculation and this would be something like 0.5 MeV. Now, the barrier height is increased, that is one. Second thing, if it falls to the ground state, if the daughter nucleus is created in the ground state and if it is created in the first excited state, what happens to that Q value, energy available to the alpha particle? That energy available will decrease if it lands up in the excited state. Right. The difference in the energy of the parent and nucleus, that is available as kinetic energy to the alpha particle and the recoiling nucleus. So, now the available energy is decreased and therefore, the Q value is decreased. So, barrier height is increased, Q value is decreased and therefore, this will become difficult. So, lifetime will increase, the probability will go down. So, it is possible it can go to all these states. So, you can have if you collect large number of alpha particles, then most of them will be like this, and but they can also decay to all these things, but the probability will be much lower. I will show you some actual results on the PowerPoint. Just look at it. Here, look at this diagram. You have this is for the parent nucleus is 244 cm, this is 244 cm and the daughter nucleus is 240 pu plutonium. Both have ground state 0 plus, this is 0 plus and here this is 0 plus. and then the rotational energies levels are there. The first excited state here is for at 43 keV, if you can read there, 43 keV and 2 plus. Then the second excited state is at 142 keV, 4 plus. Then you have 296 keV at 6 plus, and so on. The alpha decay from the parent nucleus ground state to this daughter nucleus ground state, it is 77% of times this decay is to the ground state, but then the decay is 23% of time here 2 plus. So, it decreased, the probability is decreased, because the of this angular momentum carried by alpha particle and decrease in q value. And if you go further, the third level, then the probability is only 0.22%, fourth level it is only 0.036%. So, as you force alpha particle to have non-zero angular momentum and larger angular momentum, the probability of decay will decrease, the lifetime will of that particular or branching ratio. How many of alpha particle will go through this route and how many will go through that route. So, that branching ratio, that percentage will go down with the increase in L. I will show you yet another slide here. This is a different case. Here it is not even nucleus, it is odd A nucleus. This is Am americium 249, and the ground state spin parity is given here 5/2 minus, parent nucleus 5/2 minus. If it alpha decays, it will alpha decay to this 239 Np, and for this the ground state happens to be 5/2 plus. Okay. So, from 5/2 minus of parent state, it has to decay, if it decays in ground state, to 5/2 plus. Now, L equal to 0 is not possible, there is a parity change, and L equal to 0 will correspond to positive parity. So, from this 249 Am 5/2 minus ground state to this 239 Np 5/2 plus ground state, parity changes, and therefore, L equal to 0 is not possible. What is possible is L equal to 1 or above 3, 5, because you have to change the parity. Then the next one is 7/2 plus. This is 5/2 plus and this is 7/2 plus. So, although parity does not change, L equal to 0 could have been there, but then from 5/2 to 7/2, if the j value goes from 5/2 to 7/2, L equal to 0 is not possible. You have to work out what L is possible. So, L equal to 2 will be here also parity change, okay, 7/2 parity change. So, here also L equal to 1 will be the minimum possible. Now, look at this third level, ground, first excited, second excited, this one 75 keV, this is 5/2 minus, this is 5/2 minus, and here also it is 5/2 minus. So, if it comes to the second excited state, if alpha decay takes place and the daughter is created in the second excited state, you can have this 0, L equal to 0 alpha, and that will increase the probability, L equal to 0. Coulomb barrier, remember, Coulomb barrier will be decreased with L equal to 0, although it is going to the excited state, Q value is also decreased, but the combined effect is that the total probability branching is 88% here. So, 88% times it decays to the second excited state, only 0.16% times on the ground state, and so on. Okay. So, we will stop here and we will go ahead.